you have a phase space, and if you consider a system that starts in some particular region of the oh, sorry. So, microphone. So as I was saying, I'll start by reviewing just the general basis of classical stat mech, which is you have a phase space, and you imagine starting a system in some particular region of the phase space, but rather rapidly this region elongates and round, and so a thermalization time later, it looks much more like this. And so in particular, two initial systems that are close together in phase space end up very far apart. And they have to very rapidly, separate this, and so there is this strong sensitivity to initial conditions, typically exponential sensitivity to initial conditions. So this is Lyapunov behavior, and it's specifically this Lyapunov behavior, this exponential sensitivity to initial conditions, that I'll be talking about. So this is central to why thermodynamics works. We've known for over 40 years that black holes are thermal systems. They obey thermodynamic laws. But it's really only been in the last year or two in these papers here and various ones in between that the question has been asked, what is the associated chaos? What is the associated chaotic behavior of the black hole? So what I want to do first is to just, again, present the general ideas. And then what's new here is the work of Schenker and Stanford and Kitaev, who have pioneered this, has been focused on eternal black holes in cavities, either single black holes or pairs of black holes that are entangled. And I want to extend this to black holes that form and collapse and then evaporate. And then there are some puzzles that this raises. So one can quantify this sensitivity to initial conditions by asking how much does the position at some later time t depend on the initial position. And we can write that as a Poisson bracket. I think it's this way. And in the quantum theory, that goes over to a commutator. Now, quantum mechanics is linear, which means that if two states start out nearly parallel in Hilbert space, they remain nearly parallel forever, of course. But two states can be orthogonal mathematically, but still physically similar. So if we quantize a little bit, h bar is small, the Wigner distributions are there, but they're non-overlapping, and these two states will physically separate as the system evolves.
Sorry, so you meant Q with P?
No, Q with Q initially is 0, but after some time, Q with Q is also non-zero. Yeah, any two. Yeah. Q of T with Q of 0 will, because this is the Heisenberg equations. Q of partial Q of T, partial. Oh, sorry. This is sorry. I'm sorry. I wrote. I'm sorry. No, yeah. That's. This derivative is that Poisson bracket is that commutator. Did I get it right now?
No, I think it's Q of T with P0.
Well, they're all. I mean, no. This one is not. This one is large also. If I.
T is upstairs, and so you should have a Q of T in the bracket.
It's a bracket of Q of T with P0.
Yeah.
Oh, I see. Well, I see. I'm sorry. Apologies. Can't believe it's one equation in and I'm already out of control. Apologies. You know what I meant. God. Okay. There. Okay. Thank you. I'm sorry. So that's what this commutator is looking at. And a useful thing to look at is to average over the thermal ensemble. And to avoid cancellations of phase, we'll take the absolute square of this thing. So and I've renamed Q and P to more general operators W and V, which is the standard notation in the references, because one might be talking about a spin system or anything where the variables aren't naturally Q's and P's. And so this is in particular, well, in Kitaev's talks here and in the talk that Douglas gave earlier in the program, this was the object he considered. So this is the sense in which it is measuring, well, this is one sense in which it's measuring chaotic behavior. So if we consider now an example, what's going to happen is, so this is this object as a function of time. And if we start out, say, with W and V being maybe spins that are separated so they commute, oops, the commutator will start out at 0, take a little while to get going, and then get larger, and eventually it will approach some asymptotic value. And there are two exponentials in that curve. There is the exponential approach to equilibrium, which is, as I understand from Mark Srednicki, those exponents are the Ruel resonances. And then there's this exponential growth that I've been talking about here, which is the Lyapunov behavior. The Lyapunov exponent, or times 2 because it's squared. By the way, just an aside, in the classical system, you can take this initial separation to be arbitrarily small, and so you can see arbitrarily many e-foldings. But I think it's true that in quantum systems, because there's a minimum sort of separation of the packets before they start to separate, there's a maximum number of e-foldings that one will ever see in this Lyapunov region. And so now that's everything I know about chaos, and I hope most of it's true. But now I want to apply this to black holes and to ask, how does this apply to black holes? And so with black holes, there are actually two exponential behaviors that are of interest. So here's a black hole horizon. Here's an observer or a clock falling through, and they have a proper time tau. And there's an observer in the asymptotically flat region, and they're sending out periodic pulses. And because of the geometry, the observer only sends out a finite number of pulses before they disappear. At infinity, and if you're sitting at infinity, you see that observer slowing down, never passing through the horizon. So d tau dt goes as e to the minus 2 pi times the time over beta. So there's one thing, this redshifting of the signals from the observer falling through the horizon. There's another exponential behavior, which is if you have a black hole and you throw something in or perturb it with a gravitational wave, it will decay back to its hairless state. And there's the time scale for that. These are the quasi-normal modes. And so clearly in this discussion, this exponential is the quasi-normal modes. And what we'll see is that this exponential, the redshifting, is and this again is the insight of these people I've mentioned. The redshifting, the Lyapunov behavior is the redshifting. And in fact, of course, this is decaying exponential, but what the external observer actually measures is the rate of change of the asymptotic time. They measure, as we'll see, the reciprocal. And so they see this, in fact, as a growing exponential in their observables. Now,
Joe,
yes?
Isn't that a little strange? I mean, you're assuming the black hole already exists, and you're using the black hole geometry to get that decaying
That's right.
exponential. But the Lyapunov exponent was supposed to be the sort of start of that.
No. It's taking place in a thermal ensemble, so the black hole's already. This is measuring a perturbation. By the way, I should have mentioned something here. The Rouel resonances, the decay to equilibrium, you can see in any two-point function, any O of t, O of 0. You don't need to work hard to see the quasi-normal modes, but to see the Lyapunov behavior, you have to look at this rather particular sort of thing. And yeah, so it's a black hole. It's already there, and this question asks if you perturb it, how does it return? Well, it asks if you perturb it, how. If you perturb it, what do you initially see? Yes. Now, these two things, the quasi-normal modes and the redshifting, the exponents are of the same order. They kind of have to be, at least for a Schwarzschild black hole, there's only one time scale. They're the same order, but they're numerically different. This one is a pure number. This one, you have to solve a differential equation to get. So it's, some complicated constants of the same order. There's another important distinction. The differential equation that you're solving is sensitive to the geometry in the entire neighborhood of the black hole. Whereas the redshifting here depends only on the temperature of the black hole, the inverse temperature here, which is determined in terms of the surface gravity at the horizon. So whereas the quasi-normal modes are seeing the whole geometry of the black hole, the Lyapunov behavior is seeing specifically the geometry of the horizon. So there's for a long time been a question, since Maldacena, what is the signature in a conformal field theory, dual conformal field theory of there being a horizon in the bulk? And this is the answer. It's this Lyapunov. We always knew it was thermalization in a general sense, but it's this Lyapunov behavior that really cuts through the atmosphere of the black hole and sees right down to the horizon in a simple way. And that's, again, the insight of Schenker, Stanford, and Kitaev. Yes?
To what extent is this a sort of proposed interpretation versus a clear statement that we could verify? We don't really understand completely the degrees of freedom that form the black hole and so on, so we don't really know what we're doing when we're taking that trace. Good.
So I finished part one. And now I'm going to derive an identity using some assumptions, and when we get to part three, I'll talk about the assumptions somewhat more, and that's probably a time where this question will come up. Yes?
This is all straightforward. I mean, this is standard ADS-CFT, though, all this stuff, right? I mean, for the big black holes, this is their...
We see something that looks like a certain kind of decay, et cetera, but we don't have a clean identification, I think, to this day, of what these freedom are.
Schenker and Stanford explain this, right? I mean, these are CFT things, and you can do a bulk computation with them, right? Using the standard dictionary of ADS-CFT.
Well, so there's an association, but I don't think we have a clean association.
So Joe, the effect of 2 pi, is that special to Einstein gravity or more general?
I'm thinking of gravity as an effective field theory, so I don't know the answer. Maybe I don't know about. There's actually this question and that question in some ways get me ahead in the lecture, but there's an interesting point that Stanford and Schenker and Maldacena have now shown that this particular Lyapunov exponent is actually a theoretical maximum. similar to the minimum viscosity, and maybe even better because it's more provable. Where is Douglas? But how is that sensitive to questions both of string corrections and 1/n corrections?
Well, so if we understand string corrections somewhat, it makes this exponent a little bit slower.
Slower. So it doesn't exceed the bound, but it doesn't exceed the bound, but it makes it a little bit slower, right?
Yeah, and it
Right.
does make it slower.
Right. Right.
It's not that it stays the same. It does become slower.
Yeah. Yeah. Okay. Yeah, and that's sorry. Just wanted before. That's actually not due to higher derivative corrections per se. It's due to Reggie behavior.
Exactly. Yes.
I,
That's an important point.
Actually, this ties. So, by the way, it's kind of obvious. This talk ties to a lot of things that Gabriella said yesterday, and so maybe you were going to. So, please.
No, actually, it was a different question. I mean, this d tau dt has nothing to do with Hawking radiation or with quantum mechanics, as far as I can see.
That's right. That's right. Like the black hole entropy, it's a classical. Well, black hole entropy has H bars in it. This one has no H bars in it. That's right. That's right. It's.
Talk about 10 after that.
However, we are going to talk when we. Well, it has no right. It has no H bars in it, but its effects are subtle. Right. Right. Anyway, I'm not sure about the whole answer to your question, and maybe we should save that. Okay, so that's part one. And so now I want to try to extend what's already been done. So I'm going to consider, I'm going to make an assumption here. We're going to assume that quantum gravity in asymptotically flat space has an S matrix. So we can throw a bunch of stuff together, and if it has enough energy, it will form a black hole. The black hole will eventually decay. And so we're going to assume that there's an S matrix. So vacuum. So primes will always be outgoing. Primes will always be outgoing. And the F's here are wave packets. Because I'm talking about things that happen in time, I'm not going to use plane waves from S matrix, but I'm going to use wave packets that are chosen to have some resolution in time. And what we're going to find is an identity that governs the change in the S matrix when we throw in one more particle. So it's similar in spirit to things like soft theorems and Ward identities, but I don't think it's identical to that. But it's got a similar spirit. Now, first, there's kind of something which is not important but has to be addressed, which is the gray body factors. Sorry. Before I start, no good. Before I start, I should actually draw a black hole. So it's the Penrose diagram. The horizon. This is a black hole that forms in decay, so there's some early ingoing matter. And there are the global coordinates, the Kruskal coordinates. So the horizon is u equals 0. And the other coordinate is v, and the inflowing matter is very close to v equals 0. And these are related to the ordinary Schwarzschild coordinates by u is minus e to the 2 pi, r star minus t over beta, v equals e to the 2 pi, r star plus t over beta, and r star here is the tortoise coordinate. Dr star dr is g sub r. And for a four-dimensional black hole, that's just the familiar 1 minus 2g m over r to the minus 1. So this coordinate is chosen so that, this, as you can see, basically things move at the speed of light. Massless particles move at the speed of light in the r star t plane. Okay, so there's the picture. And there's the S matrix. Now, I need to, as quickly as possible, dispose of the gray body factors, but just for completeness, I'll include them. So if we go back to the Schwarzschild coordinates, or if we go to the tortoise coordinate, I guess maybe that's the one which is best for this. So for one or the other, if you look at the propagation for ingoing mode, there's an effective potential. So this is the horizon, R sub s, and this is a few times R sub s. And so a mode that comes in, again, one of my packets F, some of the time it will scatter. So there's a reflection amplitude and then an outgoing packet G, and my convention again is prime is outgoing, and some of the time it will get through. And and transmission coefficient. And so for a given packet, F is equal to R function depends on F, G prime plus transmission coefficient times H. What I really want to do is I want to zero in on the near horizon geometry. So I want to define a horizon S matrix. Maybe I'll store that here. Which is S horizon, which we've peeled off the gray body factors. Okay, so we can take that relation, we can invert to get H in terms of F and G, and so we're talking about an S matrix in which we're going to talk about, so these are particles, this has some number of incoming and outgoing particles in terms of the H modes. Using that, you can translate, and for example, an incoming H mode might have come from either an incoming F or an outgoing. So this S matrix is actually kind of a mixture of S matrices in terms of the asymptotic modes, but this is what I want to focus on. The gray body story is a distraction. Good. Now, the basic ingredient I'm going to use is a calculation by Tuft and Dre of scattering between ingoing and outgoing particles. So, yes?
Your horizon estimate, I can just think I'm doing everything far inside the angular momentum barrier.
That's right. You can think, yes. That's how you can think of it. But ultimately, this is you can in the end the identity is an identity for the S matrix seen by an asymptotic observer. Sure, this is it, but I've peeled off the part that I don't care about. Yeah.
So you think that the fact that string theory tells us that the asymptotic S matrix exists in the unitary and so on implies that this one does?
Well, so. Good. Good. So this is something I was going to discuss later, but since it's already come up a couple of times now, let me actually say what I'm assuming. It's going to come up a number of times, because on the one hand, we know, okay, we're assuming that there's an S matrix, which is in disagreement with low energy effective field theory. We know that if information is not lost, low energy effective field theory breaks down in some way. On the other hand, to do anything at all, we have to use it in places as I've used it here. And so I think the usual working assumption sort of throughout ADS-CFT is, and gravity, and gravity period, is that one can use effective field theory for processes involving small numbers of modes like this, at least to high accuracy. I should say, the identity I'm deriving will actually there's a large ratio. You can think of it as being some power of 1 over n ADS-CFT, or you can think of it as being the mass of the black hole divided by the Planck mass. there's a large number. And there are effects which are suppressed by this large number that I'm not going to try to keep track of. For example, in this scattering in and out, the different Hawking modes can interact, and that will produce a correction which is of this order, just through gravitational interaction. I don't care. I don't want to keep track of that. One could, in principle, try to keep track of that. What I want to keep track of is things which are of this small order, but are then multiplied by a growing exponential. And there are many. Those are much more special. Anyway. So we're not trying to do a calculation here of perfect accuracy. We're trying to do a calculation which is really, okay, again, sort of the leading 1 over n correction, but larger than that by this growing exponential in time factor that, yeah.
So is the black hole included in the state 0, or is that created by one of these operators?
That's created, sorry. No, that 0 is the vacuum. So as I said, I'm talking about a process in which, we start with nothing, we make a black hole, at the end of the day we have Hawking radiation. I'm going to be inserting another mode, another incoming particle in the middle there during a time period when there's a good description as a black hole. Yeah?
So sorry, the small number again was m over mv times 1 over n?
No. These are things which, they're, so actually,
So it's the,
I think it's 1 power. I think the small number is 1 power of this. But we'll figure it out as we go along. You'll see. There'll be an equality. Might be 2 powers of this. Actually, I think it goes to G. It goes to G. It's basically 1 power of G Newton, and I'm confused by how that depends on dimensionality. So the small number is sort of G Newton. And so because we're looking at a rather good. So coming back to the assumptions, we're assuming that effective field theory breaks down in this rather subtle way, but that we can use effective theory for these really very low order interactions with few numbers of particles here that I'm focusing on. And again, this assumption is made everywhere. We don't have, I think, at this point, a fundamental theory from which this can be derived, unless we could solve the CFT in ADS CFT, but it's consistent with many things. In some sense, every test of ADS CFT is partly a test of this assumption. Okay, so now we have the horizon. We have this added particle we're going to throw in. And what Tuft and Dre calculated was the scattering amplitude if this incoming particle meets an outgoing particle near the horizon. Now, if the incoming particle is, so again, these are wave packets. They're localized in time, so I can say if the incoming wave packet is on that trajectory and the outgoing wave packet is on this trajectory. So basically, there is a delay of T1 minus T0 between the time the incoming particle enters the near black hole region and the time the outgoing particle leaves it. So as a function of this time difference, as this time difference grows, they meet closer and closer to the horizon. And so the center of mass energy for this collision is then the square root of their energies, which we can assume is of the order of the black hole temperature, or we could consider other energies, but this is something of the temperature. But now times. So if it, first of all, times the square root of G00, and G00 is going to 0, and so this becomes the square root of E1, E2, e to the pi T1 minus T0 over beta. So there is this growing center of mass energy for this collision as you consider very different the big time separation. Okay, now maybe you're bothered by the whole nature of this calculation, But that's part 3. So for the purpose of part 2, as Gabriella reminded us, or told us yesterday, the effect of the ingoing particle on the outgoing one, the simplest description of it is simply a shift. And it shifts, again, as Gabriella emphasized, towards a later direction. So again, this is the horizon here, u equals 0. And as the incoming particle goes by, this mode moves closer to the horizon. I want to write down a formula here because it's actually interesting to contrast it with something from yesterday's lecture. First of all, because of the large relative energy, large boost, this incoming particle, its field is basically Lorentz contracted, and so it's basically lying in a plane coming out of the board. So the metric is the unperturbed metric plus a shock wave. And this perturbation here is, again, because of the Lorentz contraction, essentially a delta function times something that I'll call delta u of theta. And delta u of theta, again, is just the delay that this shock wave produces. And there's a differential equation, which I want to write down for this.
By the way,
yes?
one thing, real quick. So this is the weighting order effect, as you say, increase the center of mass energy.
That's right.
But certainly if you go to higher energies, there are other important contributions.
Good. In fact,
like a black hole.
it will be. This is something that we'll come to, and actually this surprised me. It's something I'll tell you when we get to it. Yes. So well, of course, I mean, part of the point in the initial picture is this exponential growth only goes on for a limited period of time before you have sort of reached the limits of phase space and start to do nonlinear things. And what we might call scrambling in the current terminology of black holes, but we're not getting into the scrambling regime. We're getting into the separation. And so it's going to be an interesting question, what is the signal of the end of the linear regime, which we'll come to. Good. R sub s is the Schwarzschild radius, delta of v, and pi sub v is the momentum density as a function of where you are on the sphere. And so one reason I wanted to mention this is because, so if we ignore this term here, this is what Gabriella showed us yesterday for the shock wave from in flat space-time. In the black hole geometry, as Tuft and Dre showed, there you can still have a shock wave, but there's this correction. This is important because, especially in d equals 4, because in d equals 4, the solution to this has infrared divergences. And this effect of the curvature of the black hole space-time actually cuts off the infrared divergences. Anyway, okay, so there's this shift, which is a function, actually, again, of how far apart you are, how far away you are. Theta here is the angle on the black hole horizon. And so there's a shift, which depends actually on how far apart the two particles are along the black hole horizon, as described by that equation. Pi sub v is the momentum density on the sphere. So it's the momentum carried by the ingoing particle. Yeah. So this should be the same as Gabriella's formula if you drop this term and if you make this a delta function, basically. Yeah. Okay. And so what this means is that if we initially had a particle in one of these outgoing packets that I've been calling H prime, then afterwards it'll be in a new packet. And so again, prime means outgoing, tilde means perturbed by a shock wave, where simply H prime tilde as a function of u, the AD, and theta is just the original wave packet, but delayed by the effect of the shock wave. Now, before I write an identity, I want to. What's happening here is really but we can see what's happening. By the nature of a horizon, a particle near the horizon stays there a long time and only peels away gradually. By this process of pushing the particle back closer to the horizon, it will be delayed. Whatever state this was originally in, whatever information it carried, say, that will now come out later. And so there's a whole bunch of these. So I should draw. There's a whole series of these modes waiting to emerge. And so the closer they are to the the closer they are to the horizon, the more delay they suffer. And there's this exponential growth in the amount of decay as you watch these modes come out. So so what you see in the S matrix then is that the modes you throw in the particle and successive modes are delayed, and the amount of delay is growing exponentially in time. And that is the specific Lyapunov behavior. Now, there's another way to think about this, by the way. This coordinate system in which the horizon stays fixed and the particle gets shifted is the most convenient for writing down the solution. But really all that's happening is you're throwing in some more energy and the horizon is getting bigger and coming closer to the particle. It's a very simple thing. It's a very simple thing, but it again has an effect on the outgoing particles, and one which grows exponentially in time, again, because of the way the redshift works. A couple comments here. One is this effect, I don't know if, what this effect is describing is actually, again, a position-dependent shift on the sphere, which is larger when you're close to the ingoing particle and smaller further away. I don't know if that corresponds specific to any specific notion of apparent horizon or not, but it's the quantity that appears. It's the quantity that appears in this amplitude.
So I think you haven't sort of stated one of your basic assumptions, which
yes.
might help clarify
okay.
things. But so if we were talking about the Hawking state,
yes.
originally calculated,
oh, that's part 3. Hawking state is part 3. Can't talk about Hawking state in part 3. This is this is a part 3 question.
That's old stuff.
This is a part 3 question. No, I really want to say this. I really want to say this because it's the precise subject of part 3. So, yes, Tom.
You keep saying delay, and it's not completely obvious that this thing is always positive from the equation.
Oh, okay. It should be positive. Oh, sorry. This is negative, positive, positive, negative, positive. Yeah, it's positive. This is a positive operator. This is negative in
correction is positive.
Those things are multiplied, the two lines are
times. Sorry, times. Sorry. Yeah. Oh, I'm sorry. Times. Apologies. No, thank you. There was several more. Don and then Douglas.
I just want to clarify. You talked about an exponential growth effect, but as in your discussion that commented earlier, what you mean is there is a regime at intermediate times that grows exponentially. Of course, at late enough times, things shifted behind the new horizon.
Well, yeah. Everybody's jumping ahead. Yes. We'll come to that. Yes. Douglas.
I don't want to be accused of jumping ahead.
It's okay. You already have.
Just to rephrase
yes.
my question.
No, I really, okay, yeah.
Not jumping ahead. Mm-hmm. You've assumed that there are particles coming out in
Sorry, this is part 3. This is part 3, Steve. No, you really have to hold this one.
Have we finished part 2?
No. We have not finished part 2 because I have to write the S matrix identity I have to write a new result. I have to write the identity that follows from these considerations, and then some of the deferred questions will will be answered at that point, and then others will be answered in the next point.
Just to be clear about part 3.
Yes?
The actual interaction in the scattering matrix here is just the influence of the back reaction on one of them. On the other one.
That's all. Which sounds kind of boring, but it is a high energy effect because the back reaction is very sudden in the frame of the outgoing particle. And so, as Douglas already mentioned, stringy effects, for example, can enter.
But you kind of made a choice of which one you're doing as opposed to which one is.
No, it's symmetric, but I'm looking at the one coming out.
You're just choosing.
I'm choosing to be on the outside of the black hole. Yes.
Assuming there are particles.
Yeah, Steve's question is a very good one, but I want to. It has its time. So here is my S matrix, horizon S matrix that I wrote down before, with the added particle here. And now, by the reasoning that I've given you, by the reason that I've given you, whatever state the particles were in, let me write the equation actually. Whatever state the particles were in before this perturbation, they're now in a delayed state. So tildes are delayed. And so we have whatever I left a gap there. There's several gaps in this equation still, but just to work towards it. Whatever occupation, if we prepared the black hole in some particular state where these modes would have definite occupation numbers, then after the particle passes through, these delayed modes will have those corresponding occupation numbers. And there's an extra oscillator here. And really, for this to be a true equation, I need to include it here. Oh, sorry, that's just H. So this, again, is the same oscillator, but I've now moved it past all of the outgoing modes. And in fact, one can do this using an identity, which I don't know if Tufte wrote it down or if the Verlindes wrote it down with Keim first. But it just says that it's kind of an obvious thing. If we move one mode past another, whichever one acts second feels the shock wave of the first, and so is delayed. And so if you use this identity, you derive that identity.
So in that equation, how many particles do we have? We have
in this identity?
Yeah, in the top line. I mean,
So as it stands, it looks like an identity for m plus n plus 1 particles, but there's a problem.
I mean, the number of particles is comparable to the number of.
Comparable to the number of, this is a process in what I call forms and decays. So it's a process in which
I mean, how do we know that this equation holds within very complicated?
Good. So the assumption, and it is an assumption, but it's made. The assumption is that for basically for subprocesses involving small numbers of particles, we can use effective field theory. That's the assumption. And
this is the fullest matrix, so it's a very large number of particles.
Right. But I'm sort of commuting these one at a time. It's a very physical effect. It's something I trust, but we can talk about whether we trust it.
So most of the effect, I mean, you have to move this through every single piece of the ingoing shell.
Well, I don't actually. I don't actually. The ingoing shell is. No, this is not. I'm moving to the outgoing particles, but I don't have to move as far as you think for a reason I'll get to. But was there one?
Yeah. So as you move to infinity, I'm trying to get a picture of what's happening because there's different times going on. Let's ask the question in terms of as viewed from infinity, what it looks like. There's 14 modes being emitted from this
Right.
black hole. I throw stuff in,
Well, the delay is, remember, the delay is exponentially, so it's
So it's not just that there's a block where they stop coming out.
No, it's not. Actually, good. This is something like, so good. So let me say my next few sentences, and that will partly answer your question. Okay. Actually, sorry, no, I have to finish the, okay, actually, yeah. So now there's a problem with this, which is that it's been pushed way too far. We've pushed the calculation beyond its range of validity. And there's an obvious breakdown, which several people have mentioned, most recently Adam, which is that after a while, it seems as though Hawking modes stop coming out entirely. Some of what I've labeled as outgoing modes in that identity are headed towards the singularity. And so this is not an identity for the S matrix. I have to fix it. Now, it's interesting. You can work out, the center of mass energy. So now this is one. So this exponential behavior can't go on forever. This is one way in which it breaks down. Another way in which it might break down is through formation of a black hole in the collision. What I learned from Douglas, and it's true, is that this cutoff happens long before the black hole forms. The energies are Planckian, but the impact parameters are macroscopic, and so the higher corrections are not large. So so there's a breakdown due to the due to this effect, and so this. Yes.
I'm confused a little by this notation.
Okay.
So the thing on the left looks like an S matrix element to me.
Okay, good. Well, it looked like an S matrix element. Good. I just told you that it's not, though, because some of these modes are actually falling into the black hole. And also, this is falling into the black hole. And so it's not.
Before we get to black holes, I mean, if this was just some
right.
black
Yes.
space
Right.
Right. I don't understand.
Well, So, right, this is not a good. So this. Let me fix this and see if that makes you happy. Adam.
Can you ask the same question in rental space where you change your acceleration? You're accelerating with some acceleration, and then you suddenly hit another rocket, and now you're accelerating more. But you continue to insist on using the old modes rather than the two modes appropriate to your new acceleration.
Sounds plausible.
And then you get the same problem.
I don't know, but let me stay focused. My time is limited. Let me stay focused on this, and because I really want to get to part 3. So the problem then is that there's a breakdown after a while. After a while, on both sides of this, there are things that are falling into the black hole at late times that are scrambling. And we don't have a theory yet of the scrambling dynamics. And so there is sort of some unknown unitary in the S matrix. And I want to simply not see that unknown unitary, and I'll do that by tracing over everything past a certain point, before the modes start disappearing behind the horizon. And so I claim, and I don't really have any equations in between this one and the next one, but I'm claiming that this should be true. So I'm forming a trace to sum over the part that I don't understand. So I'm taking what I previously had there, squaring and tracing out the modes past a certain point, and doing the same thing on this side. And I have to, again, take account the time shift of the basis. But this is my claimed identity, and I don't have as many intermediate steps as you might like. But nevertheless, I like it. Okay, so
Joe,
yes.
just explain
Yeah, it's the same notation as before, except I've taken everything coming out after a certain time and traced over all possible squared and traced over all possible final states.
There's a matrix where the indices are different in the two pieces of the square?
Let's see. The indices line up. This is this is.
Have two of the same index, so usually you win.
Sorry, two of the same. Oh, sorry. It's squared. It's squared. It's squared. It's squared.
The indices are different in the thing and its complex conjugate.
No. So to save. Sorry. Let me. To save on. Good. To save on writing, I simply wrote the diagonal element. You are correct. The indices in the wave function or the amplitude and its conjugate need not be the same. So I'm sorry, I've only written here, I would have had to just had a whole bunch more notation. So this is actually the diagonal statement. It holds actually off diagonally. There's a subtlety in, which I just realized as I was preparing this talk, in the basis dependence on the particle thrown in. This is simplest in a basis of definite angle, not definite partial wave, because the definitions of tilde depends on the angle, not the partial wave. But you can transform from one basis to another. Okay, so this is the identity, and I claim that this is true to the indicated approximation for the black hole S matrix, and that it is the way that an asymptotic observer would see the chaos, because again, each successive mode is delayed by progressively more. And again, we're only commuting past a limited number of operators. So it's focusing on effective field theory in a limited range of time. So this is why I trust it. So part three. Part two first. One more thing. You might worry that because of this, Hawking radiation will cease. But of course, there are modes that previously would not have been populated. Modes that are kind of straddling, in some sense, the new horizon, which previously would have been unexcited and now get excited. And in fact, it's not hard to argue, and in fact, I'm about to do it, that the net Hawking flux can't change. And so the new modes have to just replace the flux of the old modes. Okay, now there's things here that should disturb you. I get the impression a number of you are disturbed about this. And it disturbs me too. So there's a question, first of all, why was the work of 't Hooft and Dre sort of not really paid attention to for 30 years? And there's two reasons, one of which I have to mention. 't Hooft, in his 1990 paper, described in words the calculation I've just given you. He described very clearly that his scattering implies a relation between S matrices of the type that I've written down for you. Unfortunately, he then went on. The first thing he did is he ignored the fact that there's a cutoff on this result and tried to use it to derive the complete S matrix of the black hole. And he tried to use it, in fact, to even justify the existence of the S matrix, where, for me, as you see, it's an assumption. And so I think that people got confused by his paper because the great bulk of what he did was more ambitious, I think, than the calculation allows. But there's a second reason why this was ignored, and it's what Steve keeps wanting to say, which is the reason we ignored 't Hooft's calculation is because he's calculating a scattering that isn't happening. That is, there are no particles coming out of the black hole. The infalling observer sees vacuum, we all know. And so there is nothing to scatter off of. In the usual effective field theory understanding of the horizon, these modes are there, but they're entangled in a precise way with their nearby modes so as to form vacuum. The particle jumps in, you have vacuum before, and by the adiabatic principle, you have vacuum after. And if you had pulled this vacuum apart into modes, there's some rearrangement of modes, but its vacuum goes to vacuum. The Hawking radiation forms later as the modes move away from the horizon. Basically, it happens due to the nonlinear translation between the time near the horizon and the time at infinity. So the Hawking calculation says the modes appear later. There's nothing there. So 't Hooft has calculated the amplitude for something that isn't happening. That's the classic way of thinking. And yet now I've spent an hour telling you that 't Hooft calculation has this consequence. What can you do? So again, the issue is there's a fairly precise set of assumptions here, and the assumptions, which are, again, rather common assumptions, and we can expect them, are that we trust effective field theory for small numbers of particles and not for large numbers of particles, not necessarily for large numbers of particles. And this relation that I've written down is produced in that way. Now, I like this. I think that it has the ring of truth. It captures, again, by the general principles I began with, there should be this Lyapunov behavior visible in black hole dynamics, and this is the way that you would see it. It also fits nicely with, again, the rigorous bound of Maldacena, Schenker, and Sanford, and the model of KITP, in which one has, from the CFT side, some indication that the bulk story has some truth. Now not this particular piece of it, but the entire bulk story of chaos and the black hole. Now, as again Steve has mentioned, if we looked at this in effective field theory, suppose that 1976 Hawking was right. Effective field theory is valid as far as it could be. Then information is lost. Then these modes are in vacuum. And then, indeed, there is no effect and there is no chaotic behavior in the there's still quasi-normal behavior, but there is no chaotic behavior in the properties of the black hole. And this fits with the general point of view that if Hawking had been right in 1976, it would mean that black holes did not have the same kind of statistical mechanical properties as ordinary thermodynamics. And it's one of the reasons for thinking that black holes don't destroy information. Now,
Sorry, I didn't quite follow that. So the Schenker-Sanford calculation is just using low energy bulk physics.
the Sanford-Schenker calculation, I don't.
KITP is very non-trivial what's happening, but I mean,
It's a good question. I haven't thought about whether Hawking. I guess you say, well.
I mean,
you know,
the same physics that Hawking used, right? I mean,
perhaps.
You could.
Yep. Okay. So in this context, at least, in this context, maybe not in that context, in the one-sided case, and maybe even for the one-sided cavity black hole, but not the two-sided, you would not see chaotic behavior. Okay. So what is happening here is that what this calculation emphasizes is that if you assume that information is not lost, the modes near the horizon are carrying information. And this makes it very tangible because you can interact with that information. You can change when it comes out. You can measure it. You can do other things to it than the simple stuff that we've been talking about.
Joe, that's a particular assumption
Good.
how the information comes out. It comes out right to the modes.
Right. So one way to avoid this, well, actually, good. Yes. Let me come back to this again at its proper time. What I want to talk about is sort of an analog. So imagine, so the point is, these are vacuum fluctuations. At least if there is no firewalls, we've always thought these are vacuum fluctuations. And but these vacuum fluctuations are carrying information. They're carrying information in this very tangible way that I've described. And vacuum fluctuations can't carry information. we could try to sort of make an analog experiment where we have some mode in the vacuum. And I'm choosing it to be a mode of mixed positive and negative frequencies so that its distribution in vacuum is thermal. And we could measure that mode and put it, record its state in a register, but not destroy it, just measure it and let it go through. And then a later observer could absorb the same mode, and they could put their detector in the same state. And so clearly this mode is, what I'm describing here, this mode is carrying information because it allows the two observers to put their detectors in the same state. But this is a vacuum fluctuation. The point is, of course, it's not a vacuum fluctuation after it's been measured. This mode is a vacuum fluctuation because it's entangled with nearby modes, and the process of measurement here destroys that entanglement. And so although these modes statistically are unaffected, they're no longer properly correlated, and so you can be quite sure that if you measure the energy in this region of the experiment, you will find a flow of energy accompanying the flow of information. And in the context of the black hole, as I've described, is doing this experiment all the time, where this register is the earlier radiation, and the energy that accompanies the information is the firewall. Now, this is really no different from the very first AMPS argument. It uses the same assumptions about information not being lost, and yet the validity of effective field theory for order 1 questions with small numbers of particles. As Steve has mentioned, his scenario for avoiding the firewall is that, in fact, some information would non-locally appear further out from the horizon. In that case, my identity wouldn't hold, at least not in quite the same form. And in that case, okay, in fact, if that identity holds in any form, then there's a firewall. So you would have the, okay. So you need, good, so, yeah. Okay, so actually, I think I'm going to conclude and then that you make your comment. I didn't, when I started this, I was just, the purpose was to understand what chaos meant for a black hole, and then, okay, and then I discovered that Tut had already said the words. I didn't plan to come back around to the firewall, but I think that this discussion where you see that you can manipulate the information near the horizon really drives home what's happening in a more graphic way. One class of ways to avoid this is to suppose that this register and this vacuum mode are the same thing. And obviously that's not true in the laboratory experiment, and we can argue about whether it's at all plausible that would be happening in a black hole. So, and then there is, again, Steve's alternative. So, thank you. Yeah, you've been waiting.
So actually, one of the things you said, I'm not sure is quite right. So you said you're assuming that effective field theory holds for a small number of modes. But I think in the picture that you're stating,
yes.
You're really not assuming that effective field theory holds inside the horizon, because you've got to have some way to get the information into the modes right at the horizon. So you have a breakdown of effective field theory inside the horizon, which stops exactly at the horizon.
Yes, it's true. Yes, in fact, when the horizon expands, there are modes that were previously empty, and somehow, not much later, they are carrying information. They get imprinted. They get imprinted. It really, so, what's happening, in the old days, we would say the stretched horizon reaches out, absorbs them, and then re-emits them. The stretched horizon is like the firewall, except you can fall through it. Yeah. It's, it's in this whole subject, we're piecing together assumptions, but I do think, again, that the connection with Lyapunov behavior, I think, is really, I think, a compelling indication that this is the way things are going on. Yeah.
What's in other discussion or question?
I have a very naive one.
Yes.
I mean, would it be fair to say that what we are really considering is the S matrix in the presence of a black hole, or rather, you are looking at the evolution operator during a short lifetime, a short time, rather than the usual S matrix. I mean,
it's the usual S matrix.
Coming back to the equation.
It's the usual S matrix, but it's an identity that holds. Again, you're right. It's an identity that holds when you throw in a particle. In some sense, after throwing in a large number of other particles.
Yeah,
right. It's a theorem.
That's right. Remember well, Day and Top.
Yes.
They consider that process.
That's right.
As you said, they try to extrapolate that all the way to get rid of most of that.
Yeah, I don't see how, given the, I don't see how they can avoid the problem that the calculation breaks down. In fact, I'm surprised they didn't see it, because it's very visible that modes, are.
I vaguely remember they send in one more particle, out one more particle, and pick up an extra piece of the S matrix, and then I remember I had the same criticism that they were extrapolating the game.
But I think so I think, though, essentially, if you don't try to do everything, if you take this part as a given, you get an identity for what happens when you add one more particle. Right.
That was certainly the way it was originally phrased by the film, right? That this was like as you said, like a soft field. I mean, it's not soft, obviously, but adding one more particle to the S matrix, and we see how the S matrix changes. And, you know, the extent to which he did, have these extreme speculations, but I certainly didn't read his paper as making quite as dramatic a claim as you're sounding like, that he had actually calculated the black hole S matrix.
Well, he didn't he calculated the change in the S matrix.
Just the change.
He claimed much more.
I mean,
he claimed he had the whole thing.
He thought this kind of thing could unitorize the scattering.
Right. He wanted,
He hopes.
That's right. See, it's,
Okay.
yeah.
I think he was not making such a dramatic claim in my reading of those books.
Well, I mean, there are parts that are dramatic. We can go back and read them, but yeah. Thanks.
You made the statement that the black hole is naturally measuring some modes. Could you repeat that statement?
Just the fact that for an old black hole, the outgoing modes are entangled with the early ones, and so effectively, all of the outgoing modes in an old black hole are tagged. Tagged by their, that's what I mean. Right. Because the infalling observer is falling through modes that are carrying information, and this makes it very tangible because they affect that information. Transfer of information implies transfer of energy, and it's happening in every mode that you're passing through. What if there's an octopus? It's a very Stanford question. What if there's an octopus? I don't know. You mean?
Didn't he just spoke to them?
Well, So as I said, what I said is there's no octopus in the laboratory example. Maybe there's a black. Well, we're going to talk about why there's no octopus, right? Yeah.
Other questions or comments?
So this calculation, it applies sufficiently late.
Good. So the identity. Good. So the identity would hold if we actually simply added one more ingoing particle in a sequence with the earlier ones, but again, there's a time. So there's a if the particle that we throw in is thrown in the first half of the life of the black hole. So this, good. And the black hole is in a typical state, then there may be no observable effect. That's something I have to think, yeah. If the black hole is in a typical state and it's thrown in the first half of the life, there may be no observable effect. That's a good question. There's a question of the readability of things. So yeah, there's still, because once you throw that particle in, past a scrambling time later, you've completely changed the subsequent S matrix. So it's observable only if you can read it off from the earlier modes of the black hole. Now, I think if you prepare the black hole in a special state, then you can read it out even early on. It's similar to words one would say with firewalls. If you prepare the black hole in a special state, then you can read it out even if you throw the particle in very early in the decay. But if the black hole forms naturally, then if you throw it in the first half, there is no way to read the information out. Let's say, for example, you prepare a state which will be a number eigenstate of the outgoing modes. You form the black hole, right? You form the black hole in a state like that.
But in general, this calculation will only apply when you think about particles that are infalling after.
Yeah, I think the identity is still true, but doesn't carry any information in generic. Yeah. I think the identity is still true, but to ask about. But again, to see something, an implication of it, you would need to ask a non-generic question. Yeah, it's a good question. Yeah.
To follow up, the hypothetical free-falling observer.
Yeah.
Does not mean
Pardon?
any. Right? I mean, is there?
Well, so good.
Contradiction with the overview?
Well, something contradicts with something, but I'm not especially comfortable giving up the idea again that I can send information through your body without sending energy through your body. And if you have an infalling observer, I would stick to that principle. So it says that if we try to stick with our assumptions, no loss of information, and order one correctness of effective field theory outside the horizon, we lose effective field theory rather abruptly at the horizon. Yeah. Now, it's interesting to ask, could the identity be true, the chaos be there, and the interpretation be wrong? And yeah.
I'm trying to understand to what extent you have an identity within effective field theory. So you have this sum over final states.
Yes.
And I guess we don't know really how to characterize those final states without going outside of effective field theory. So is there an implication? I mean, is there still some content in that equation?
It's like an inclusive cross section, meaning inclusive, exclusive cross section. You measure semi-inclusive. You measure the presence of some particles, but not the rest of the decay. Yeah,
you have a basis for final states. You just don't have the unitary that gets you there. Right?
Yeah.
Because everything's decay.
Maybe let me comment on that. So you did this thing where you did this tracing out.
Yes.
And so usually when you do that, that gives you a quantum channel that's not unitary. It's a sort of more general map from, that can go from pure states to mixed states.
Right.
But the claim here would be that actually it's still a unitary.
Good. Right. So in fact, that the equation where I didn't write down all the indices can be interpreted as a map from the initial density matrix to the reduced density matrix for the set of particles we're looking at outgoing. And as you say, such a thing need not be unitary, but this one is. I guess one could ask whether it has consequences that even without not knowing anything about x, the thing we're summing over, it's not clear whether it has consequences. Yeah.
So you disposed of the gray body factor at the beginning.
Yeah.
That was fine if we were doing just sort of linear quantum field theory on a background space. But these
backwards from Scry
Mhm.
to see where did this mode come from? That's the Hawking mode. It's, you don't make it all the way to the horizon. There's quantum gravitational interactions in the vacuum, so that this whole analysis you did seems disconnected from infinity by
Good.
strong interactions.
Are you saying there are calculable strong interactions that would correct this?
Absolutely. Yeah.
Which are?
The field equations are nonlinear, and it becomes highly nonlinear. If you just take two modes in the vacuum and try to evolve that, by the Einstein equation, there's going to be some large center of mass energy near the horizon, and it'll be.
Well, I think that's exactly the part I've kept.
But you're going from the wrong direction. You're starting at the horizon and propagating out. But you should be asking, I want to know what's the S matrix for something coming out at late times. I should trace backwards from the late time thing I'm seeing and find out where it came from.
I think it's the same.
Your calculation.
No, I think you will. I don't think anything will get in your way. Because I mean, what I've calculated. First off, I think I've calculated the effect that you're talking about, or all these other folks have, and the interesting thing is that the observable effect arises before gravity gets strong.
Joe, just to translate, Ken's asking about effects having to do with interactions between outgoing particles.
Between outgoing particles. Good.
What in your language are outgoing?
Good.
Is that right? Yeah, what are you thinking about? If you trace back, what interaction are you thinking about? I'm saying you can't think of free field theory, the vacuum, especially if you neglect the barrier, is just a kind of right-moving and left-moving stuff passing through each other freely. But really, we have an interacting field theory, and that's just not the way it's working. So if I trace it back,
He said large impact parameter. Before, right? He said he was going to ignore things that were suppressed by powers of unemployment. And I think the claim would be that everything that you're talking about, I mean, it's there, but it's suppressed by powers of unemployment compared to the thing that it's keeping.
That's what I would have said. Yeah, I would be. It'd be interesting if there's something which is not suppressed. But I think.
Calculation actually now by Renaud Parentani that tried to actually address this directly, which I can show you later. I don't know to what extent it was successful. It looked like the correct first step to me.
Okay. Look at that.
Anything else? No? Okay. Well, thanks again.
Sorry for postponing this, Steve, but it was exactly the thing that comes up at the end, the assumptions. Yeah.
Yeah, although